Hi, everybody. I guess you're wondering why I'm wearing this patriotic bandana. It's not because I've always wanted to be a pirate. It's partially because I don't want to do my hair, but it's because I'm really psyched up to talk about ionic bonding. This is the stuff that you guys get excited for when you first take integrated science because you learn that you're going to do chemistry and then you like, let's throw some chemicals together and explode stuff. And you guys are asking me questions like that. And I'm like, yeah, we're not going to explode stuff because that's not really safe. Maybe we'll do some explosions. I don't know. But what we're going to do is we're going to take a look at the Lewis dot structures. And remember, the Lewis dot structures only show valence electrons. So this first one is magnesium. And you can probably guess that magnesium is in group 2A because it has 2 valence electrons. This is fluorine, or fluorine. Fluorine? Different people say it different ways. Fluorine is in group 7A because it has 1, 2, 3, 4, 5, 6, 7 different electrons. And this one this is oxygen, and it's in group 6A, 1, 2, 3, 4, 5, 6. So we're going to start out and we're going to take a look at what would happen with these. So ionic bonding is all about ions. And in the previous video, you guys should have learned that an ion is just a charged particle. These different elements can become charged either by gaining electrons or losing electrons. So when they do that, they're trying to get a full octet. And if you take a look at magnesium, it has 2 ways of doing that. Now remember, this is the valence shell. Magnesium is in period 3, which means it has 3 shells. Magnesium could either drop these 2 and just go back to its second shell, which is already full, and then be happy. Or it could gain 6 more different electrons to have a full third shell. The easiest thing for this thing to do is just drop the 2. All right. If you look at fluorine, I don't know. Fluorine has 7 valence electrons, so it could either drop those 7 or it could just gain 1 more. The easiest thing for it to do is to gain 1. Okay. Oxygen, it has 6 valence electrons, so the easiest thing for it to do would not be to drop these 6 to go back a shell. It would be to actually gain 2 more. So this thing would want to gain 2. Now, as we do this, these things, this is an electron donor because it dropped these. This is a metal. These 2 guys are electron acceptors or recipients. This is a nonmetal. This is a nonmetal. An ionic bond, we're going to find out here in a second, always happens between one metal and a nonmetal. Okay? So that's one sure way for you to look at something and tell whether it's an ionic bond or what we're going to talk about later, covalent bond. A metal and a nonmetal. There's one weird thing to this. The metal could be joined with this thing called a polyatomic ion, which acts as our nonmetal. So a polyatomic ion. And a polyatomic ion is just a charged particle that travels as a package. So examples of that would be things like cyanide, which has these carbon and this nitrogen travel together and they have a negative charge overall. Other ones that you might look at, the hydroxide ion, an oxygen and a hydrogen travel together and they have a negative charge. So those are polyatomic ions, but again, they act as this non-metal right here. So we're going to actually now get into the bonding portion of this. We could take magnesium and we could bond it with any non-metal. Well, don't quote me on that. Not any, but these 2 we could definitely bond it with. So magnesium has 2 electrons, so we're going to drop its 2. Okay? And when we do that, magnesium becomes a +2 charge. All right? Since it dropped those 2 electrons have to get picked up by something. Okay? So here's what we could do. It would be really easy for oxygen to just suck those 2 electrons right up. Okay, so they came from over here. There was 1, 2. If they were able to make their way over here, oxygen would suck them up, have a full octet, and then we would also have a -2 charge for that. Okay? Magnesium and oxygen okay? This is kind of how we write it. We write them in brackets there. And then the oxygen, okay? This is the Lewis dot structure for what we call magnesium oxide. And we'll talk about naming ionic compounds in a little while. This was a pretty easy one. This had 2 to give away. This needed 2. It's like a perfect partnership, okay? I'm going to show it a little bit differently with Lewis dot structures, okay? Magnesium has those 2. Oxygen has space for 2. Oh my goodness, if they lock, it's like a lock and a key, okay? So that's a pretty easy one. What we're going to take a look at now, though, is what if we didn't have a nice easy one where it was like this one had 2 to give and this one had 2 to get, or 2 to receive. We're going to take a look at fluorine, okay? When you look at magnesium and fluorine, they can also combine, but you get rid of that one because it traveled over there. We still have this problem of magnesium still has 1 that it has to get rid of. So what we could do is we could have another fluorine atom, and it can take that other one, okay? And now it comes over here. So these guys are now happy because they have a full octet. Magnesium's happy because it's went back a shell, which was already a full octet. And then the way we would write this out, I've seen different people do it different ways. Here's kind of how I would write this one. I would write an Mg, and I don't always do the brackets. For some reason, I'm just feeling like bracketing stuff in. Maybe it's the bandana cutting off circulation to my head. I don't know. And then here's the other one, fluorine. Remember, because it picked up an extra negative charge, it has a -1 charge. And then we would put the other one over here. 1, 2, 3, 4, 5, 6, 7, 8. And you have a fluorine and then a magnesium that's a 2+ charge, and then another fluorine that has that negative charge. And if you look at this, see, I didn't always write the 1s either. If it's just a minus, sometimes you can get away with just not writing the 1 charge. If you look at this, -1 + 2 -1. This thing will have an overall charge of 0, and that's what ionic bonding is going to give you, okay? You're transferring electrons, so ionic bonding is about transfer of electrons, and the ions attract to one another through just kind of this electric attraction force, okay? So they are electrically charged, they attract to one another, and based on how much charge they have, they will combine in different ways to form these different ionic compounds, all right? Now, the way we would write this one in particular, I forgot, since it has 1 Mg, you would write Mg, and then since we have 2 fluorines, we would write that with a little 2 next to the F. So Mg F sub 2, that little sub tells you how many of these, this particular element we have in the compound. So we have 1 magnesium, which we never write that 1 right there, okay? And then we have 2 fluorine atoms, okay? That's why that F2 is right there. So we're going to try another one real quick. I'm going to give you guys 2 different things, so you'll need to look at the periodic table to do this. All right, let me erase all this. We're going to look at aluminum and oxygen. So, looking at your periodic table, here's aluminum. Okay, it's number 13 on the periodic table, has 3 valence electrons. And oxygen, which has 6 valence electrons. So, aluminum, 1, 2, 3. Oxygen has 1, 2, 3, 4, 5, 6. I want you to see if you can figure out how these things would bond together. All right. All right. So looking at aluminum and oxygen, they do have the ability to bond together. It's probably one of the trickiest combinations that we can give you. So here's how you take a look at it. Aluminum needs to either drop 3 or gain 5. It's probably easier to drop 3, okay? Oxygen, however, wants to gain 2. We already went over that. Again, metal, non-metal. This is ionic bonding. So as we go over this, this would be able to drop 3, which would have an extra 1 left over. So it could give 2 to this one, but then we've got this other guy just kind of sitting out here. So we need another aluminum. Or sorry, not another aluminum. Another oxygen. 1, 2, 3, 4, 5, 6. It picks up this one. Okay, that's the one that I just drew there. Oh, but it's still not stable. So these guys are stable. This has a +3 charge now. This has a -2 charge now. This has a -1 charge, but it's not stable. So what we need is we need to add another aluminum. Okay, and it's got a not a +3 charge. We've got to give it its electrons. Remember, it has those 3 electrons originally. It can transfer 1 of them over here. So now this is a -2 charge. Get rid of that electron. Again, it had 1. It transferred over to this guy. Aluminum is now a +1 charge, but it's not happy. It is not stable. It wants a full octet. So what we need to do is we probably need to eject these other 2, which means that we're going to need an oxygen to pick them up. So let's draw another oxygen. And take a look at this. These 2 electrons right here, they can get picked up by the oxygen. All right, I'm going to draw that out here real quick. So those 2 electrons leave there. They get picked up by oxygen. Oxygen gets a -2 charge. Aluminum gets a +3 charge. All right. So in the end, after all that kind of guess and check work that I just did, what you would end up getting is this element. Aluminum, there's going to be 2 aluminums. I'm having trouble counting today. I was looking at the charge instead of the number of aluminums. There's 1, 2 aluminums, Al2, and then there's going to be 3 oxygens. So Al2, O3, aluminum oxide. And again, we'll talk about the naming here in a little while if you haven't picked up on it. Aluminum oxide is a tricky one because you have this back and forth, and that's about the most back and forth you could really go through for ionic bonding. There's an easier way for you to do this, though. And some teachers don't like this because it doesn't help you actually understand, but if you just watched my video, hopefully you understood kind of the physical process of what's going on. So there's aluminum, there's oxygen. Like we said, this one can gain 2, this one can drop 3. If we wanted to figure out how many of each of these elements we needed at the end to make the ionic compound, we do this thing called the cross multiply rule. I have 2 open spaces here. I'm going to cross that over here, and that would mean that I need 2 aluminums. I can drop 3 over here, so I'm going to cross it over this way. Okay. That means I need 3 oxygens. And take a look. This is the same thing that I got over here. All right. That cross multiply rule, it's maybe not the best thing for you to do right off the bat, but after you've practiced this a while and you've kind of figured out the ionic compounds that you make and how they form and everything and their ratios, then you'll be able to better do it. So other things that can combine with one another. Let's take a look at like lithium oxide. LiO2. Lithium has 1 valence electron. Oxygen. Oh, I wrote this wrong. Ooh. Lithium and oxygen. Sorry. Lithium has 1 valence electron. Oxygen has 1, 2, 3, 4, 5, 6. All right. If I wanted to do that cross multiply rule, I can drop 1 from here. So that means I need 1 oxygen. Oxygen can gain 2, so that means if I cross it over, I need 2 lithiums. All right. So this is what you would get as the compound at the end. Lithium oxide okay, Li2O, lithium oxide. I'm going to show you again how that actually works out for the whole Lewis dot structure. 1, 2, 3, 4, 5, 6 for the oxygen. Lithium only has 1. It can transfer that to that oxygen, but we still have this open space right here that we need another electron for. So that means we could probably have another lithium. Here's the electron, and this electron could go in there as well. So we would have 2 lithiums with positive charges, okay, and an oxygen, 1, 2, 3, 4, 5, 6, 7, 8, that has a -2 charge because it picked up 1, 2 electrons. And this is kind of the Lewis dot structure that you would have for that, okay? So big things to remember. At the end, your your compound needs to be electrically neutral. All right. We're going to do one with a polyatomic ion as well. Boom, boom, if you need it. Again, polyatomic ions are just ions that travel as a package. Whoops. We're going to do this one called the hydroxide ion, which has a negative charge. Okay. It's an oxygen and a hydrogen that travel together. And we're going to combine that with aluminum, which again is a +3 charge. So 1, 2, 3 valence electrons. So it would form a +3 electron once we drop all those, or sorry, a +3 element particle once you drop these 3 electrons. Okay. Oxygen, hydrogen. Again, this would have a negative charge. We're going to do that cross multiply thing again. This is only 1, so that means I need 1 aluminum. And then I got a +3 charge here. I'm going to take that 3, go it over here. And in parentheses, I put the polyatomic ion. If you need multiples of a polyatomic ion, you put them in parentheses like that. And then the sub 3. That means that we have 3 of this package, this polyatomic ion altogether. Let's make sure that the charges work out. We have 3 negative charges. We have 3 positive charges from that aluminum. All right, so that would make a nice little aluminum hydroxide. If you have any questions, please let me know.